Alright, today's lesson is pretty short.
Ready for my
But do you guys have your books on you?
Yeah.
Open your books to page 161, please. We're going to read, before we talk about Pascal's principle, we're going to talk about one of the cooler creations that God has created, known as the octopus. Octopus? Octa. Eight. Food is also ethnic. Ethnicity is just people groups. Yeah, a people group created a food, right? So isn't all food ethnic?
But God created the octopus, and the octopus is not enough.
Alright.
Stop.
So, everybody, hey, everyone on page 161. Okay? I'm going to read, I'm just going to restart from the top and probably read this whole page here. Okay, it says the octopus is among the most intelligent invertebrate animals. It also has excellent eyesight and sophisticated defense mechanisms. You can shoot rockets. Okay. One of these mechanisms is the ability to move rapidly away from harm using a process similar to that of a rocket engine. The octopus draws water into its internal cavity and then rapidly shoots the water out through its siphon, a tube-like structure. The muscular force exerted on the water in the cavity is used to accelerate the octopus. This action is similar to squirting water out of a full sports bottle. The force applied to a contained fluid in one location is transmitted through the fluid to another location. So the force that it shoots the water out gets transmitted through that siphon-like tube and propels himself forward through the force applied on the water. Similar to when a rocket shoots off, okay? The rocket shoots off a bunch of energy downward, and due to Newton's third law, what pushes back on the rocket? Yeah, but what is pushing back on the rocket, do you think, in this context? The air. Did you guys realize that when a rocket shoots off, like it shoots stuff downward, why does it go up? Because of Newton's third law, every action is an equal and opposite reaction. So the rocket pushes down in the air, and the air pushes back on it, causing it to propel upward. Same idea here with Mr. Octopus. Okay, this observation was first explained by Blaise Pascal. In a famous experiment, he attached a long, narrow pipe to the top of a tightly sealed, water-filled gasket, and that's what the visual on the right is showing you. Okay? A relatively small amount of water that filled the long tube above the casket provided enough pressure to burst the cast stays. Basically, that was an enclosed barrel, and what did we say primarily determines water pressure? Depth, okay? So height and depth are kind of interchangeable here. Does that make sense? So it didn't matter how much volume was above it. All that mattered was how high it was above it. And pressure and force is distributed throughout the whole volume of the water. Let's keep reading here. From his experiment, Pascal reasoned that changes in pressure on the surface of a confined fluid are exerted equally throughout the fluid at all points in the fluid. So if I apply a pressure on the top, it gets distributed all the way through the fluid and at all points of the fluid. Okay? This statement is known as Pascal's principle. However, there are several conditions that must exist for his principle to be true. First, the fluid must be confined in a completely enclosed container. If it wasn't completely enclosed, wouldn't the fluid be able to leak out in some way, shape, or form, and that would change the pressure a lot? Okay? If not, any change in pressure would cause it to move out the opening, similar to a sports water bottle. Second, the fluid must also be incompressible. Why? Wouldn't increasing the pressure of something that could be compressed, wouldn't that just change the volume? Okay, and we'll find out that there's a relationship between pressure and volume later on in this chapter. Okay, in other words, it cannot absorb pressure changes by allowing its particles to be squeezed closer together. For practical purposes, the only real fluids that approach this conditions are liquids. Gases are far too compressible to completely obey Pascal's principle. So, your first notes are his principle and then the conditions that must be met for his principle to be true. Okay, and we only have one more slide after this. We're done. I'm going to because of fluids, the fact that fluids are touching, and the fact that fluids flow, if you change the pressure at the surface of something, it gets distributed all the way through the whole entire fluid. And there are some really important practical uses for this principle, which I'm going to show you on the next slide. And this will also kind of build on something we talked about last chapter. Nice having your own kitchen in here, huh? I'm gonna make some ramen with that. I do what I want. This is forte. Okay. This is an application of Pascal's principle. I'm going to kind of show you how this works. You guys know what hydraulic machines are. Anybody give me an example of an hydraulic machine?
Hydraulic press.
Okay. What is that used for?
Crushing.
Okay. Any other example of a hydraulic machine that you've seen? What? Really? I didn't know that. It's new news to me. Is it?
No, this is used to look at the time.
Oh, that's just like a car jack. That's what I would call it.
Yeah, but I've seen
Oh, gotcha. Anybody ever work on their car? Probably not. You don't even have a car, do you? Seen a parent work on their car where they have to use the jack to lift it up? Right? I mean, essentially, you guys, like, when you lift up a car, don't you exert a force to, so essentially you're lifting up the car. You realize that's pretty wordy. I'm going to kind of show you a visual on how this works. It says it's a machine filled with a hydraulic fluid, that uses Pascal's principle to do work by converting a small force exerted on a small diameter piston to do a large force exerted on a large diameter piston. Do you guys know what a piston is? Minecraft? There's piston in Minecraft?
Controlling electricity.
A piston would look like a square? Square piston?
Google it.
I suppose you could have a square piston, probably not the most efficient, but
Everything in Minecraft is square.
I get it. Yeah, that's why I said that.
Except shadows. Except snowballs.
But,
The snowballs are still.
okay. I'm going to try my expert drawing skills, since I'm really good at drawing. Yes? What is it to you?
Everything.
I don't know. But, I'll show you. Alright, so I'm going to draw up here. You're probably going to want to draw this as well. I'll do my best to draw a decent looking picture here. Wow. Something along the lines of that. Yeah.
It's in the book.
And we're using this to lift some object. We'll call it a car.
Oh,
It's a truck, whatever. There you go. And
I'll
light.
pop the door back.
Perfect. Okay? And then what we have in here is fluid. Okay? There is specific hydraulic fluid. Usually the specific fluid they use for hydraulics are fluids that don't have a lot of friction. Okay, because if you use a fluid that's really good at flowing, it does not have a lot of friction, you're not going to lose some of your energy, right? Because we know that energy is never created or destroyed, but it can transfer from one form to the other. So if it's lost in the form of friction, it's not going to be used to do work. Does that make sense? Okay? Now, we said that for Pascal's principle to be true, what two things need to be the case here? It must be enclosed, okay? So in this particular hydraulic system, I've got fluids in here, okay? Is it enclosed? Okay? What's the second thing? Must be incompressible, so we need to use pretty much a liquid, okay? a piston, Rose, is, it's hard to describe without just using a visual. That's a piston and that's a piston. How do you describe a piston?
Like Google it. Have you ever seen a syringe for like this? The little thing slides up and down and squirts the fluid out the end. That's a piston.
It's basically something that is enclosed that can slide up and down, so it's not fixed. Yeah, so I'm going to push on this and it's going to slide down the piston. Okay? So if I have fluid in here, if I apply a force on this, since this is an incompressible fluid, what's going to happen to this piston? It's going to go up. So this piston is going to go down. This piston is going to go up. Okay? So, what I'm going to do is I'm going to take this piston and I'm going to push it all the way to there. Okay? Now, that fluid, this is going to displace some fluid, right? Okay, which is going to cause this to go up. There is an area here. We'll just call that A1. That's going to be equal to the amount of that this is displaced. Okay? Now notice how this is a bigger piston. So is it going to rise as far? No. So let's say it rises to like here. But did the volume of this and the volume of this, that should still be the same. Does that make sense? Because what I displace here is just going to be the change over here. It's just going to look a little bit different because this is a smaller piston and that is a bigger piston. Does that make sense? Okay? So what we have is our change here. All right? Now, we know that if I apply a pressure here, I'm going to get a pressure there. Okay? But notice how far this piston moves. From here to here. Make sense? And notice how far this piston moves. What do you think we're using? What was that? A simple machine. And what principle do you think we're applying here? The distance principle. So, if anybody ever jacked up your own car or jacked up a car, right? You're just like, and like the car's barely moving, right? That's because you're moving a long distance. You're only getting a small distance out, and the reason why is so that your force is less. So that is exactly how hydraulics work. They just use the fact that in a liquid or in a fluid, the pressure I apply here gets transmitted all the way through the liquid and up to the other side. So they use the properties not only of a simple machine, but they also use the properties of fluids with its ability to transmit pressure and forces in all directions through the fluid. So there's a lot of applications for pistons. It's really just a modification of a simple machine. Right? Now, the more distance this moves, the less distance this moves, the easier it becomes. So usually the effort piston is bigger or smaller than the resistance piston. It needs to be smaller. Okay, so this is our effort piston. This is our resistance piston. The area A1 should be equal to the area or volume of, I should probably say volume instead. That's better. Because it's the area of the pistons times the height it moved. Area times distance or height is what? Volume. So I'm going to say volume instead. That's a little bit better. So we'll say V1. V2, and they should what each other? So, how hydraulic machines work, okay, is you have different sized pistons. Okay, the smaller piston has to travel a lot further than the bigger piston does, using the distance principle to make work what? Questions? Any? Come on, do that. Here, all of a sudden got real happy.
Just one hand.
Practice take like 7 hours.
Yep.